All right, now it's time to capture the data. After you've done all of your investigation, Mr. Holmes, you're ready for a reproduction plan, which is going to be so easy because you've already done the heavy lifting for that. You got to figure out where in the network are you going to capture to get the data that you need, how are you going to capture it, and then I'm going to finish off with some capture tips. So, reproduction plan, again, this is the easiest part because this is based on all the work you did in narrowing down the problem. You should know when it happens, how it happens, what it looks like, or how intermittent it is. Based on all of those factors, you're going to come up with a plan to test and reproduce. So if it is something that you can sit down with the user, you can have them reproduce the problem and capture the data, you're just going to test and capture. Done. However, if it is something that's intermittent or you're capturing in the network where there's a lot of bandwidth, then you're going to be looking at a capture and wait situation using rolling captures, and we're going to go into that later. So on where to capture, I like to capture close to the source of the complaint. So Ricky Joe Bob is complaining about whatever application, slow getting his fish pictures down, and I want to capture close to him. I want to see the problem from his perspective so I can see the round trip time from his perspective. I can see the packet loss and maybe packet reordering, whatever it is, I can see it from his perspective, and closer to him, I can capture all the traffic without a filter. Further into the core or the backbone, does anyone use that anymore, of the network, I'm going to maybe have to figure out a smart way to get the data because there's just so much of it. Now, if you can't do that, you could capture near the server. Ideally, it's a server you own or a server or two or whatever. The application servers or something you own, you can capture near them. If it's something out in the cloud, then capture at the edge of your network before you hand off. And the best case scenario is you capture from both ends. That's how I like to do it. I want it from both ends so I can see both sides of it, and I can see things and I can correlate things that I would not be able to see if I were just capturing from one end. So if you can capture from both ends at the same time, and make sure that your capture devices, that their times are in sync. Use NTP, people, it's your friend. Now, how are you going to capture the data? You can do this on the client machine, you can do it with a span port, you can do it with a tap, you can do it with a hub. Oh yeah. All right, on the client machine, this is where you can just run Wireshark or T-Shark or TCP dump or dump cap or win dump. You can just run it right there on the client machine where they're having the problem and get the data. You just have to sit next to them and look at the pictures of their, ugly kids or whatever. So the pro here is that there's no extra hardware, there's no infrastructure changes, there's nothing else you need except some software and to sit there with their machine. And on the downside, if you have a security policy in place that you can install apps, you won't be able to do it potentially. You could try doing a portable app on a USB key, maybe. But the biggest issue here is you're not actually capturing what's on the wire. So let's talk about that. So from this diagram, we can see that when an application, say such as a web browser, wants to send data across to the other side, to the server, what it's going to do is take a chunk of data, let's just say 4,380 bytes. It's going to hand that off to the kernel, which is the TCP IP stack, and let then the TCP be responsible for getting that data to the other side. So it sends this data down, and when we're capturing data with Wireshark or TCP dump, the library that's used called libpcap or winpcap sits in between the kernel and the NIC driver. So this data is grabbed here and sent over to Wireshark, either saved on the disk or displayed in the Wireshark UI. Now, TCP IP needs to break this up into the appropriate size chunks of data that can go on the network according to the MTU. But we have something called segmentation offload. This is a feature in modern operating systems and NIC drivers that instead of TCP doing it, the NIC card does it, and it is a performance boost so that we offload this to the hardware on the card. So this data goes down here, then the NIC breaks it up into, say, 1460, which might be the MSS, the maximum segment size, and off it goes. So now you can see the problem here is that when you're analyzing this and you're looking at the data in Wireshark, you've got one big packet, but what was really sent on the wire is 3 smaller ones. So due to issues like segmentation offload, there's also a checksum offload. So the NIC itself will do the checksum and then write it into the packet. You're not getting what's actually on the wire. You can go into the NIC driver settings and disable some of these offloading features, but now you're changing variables. You're changing the domain of the issue. This is not an ideal situation for when you're trying to analyze a problem. All right, another way that you can get the data is with a span or mirror port. This is